So far when we talked about sets, we say that we could combine the sets together by taking unions, intersection, taking complements, and also given a set we can find out if something is an element of a set, if one set is a subset of another, and what is the size, that is cardinality of a set. There are a few more things that you could do with sets, well, quite a few things, but we are going to look at just several of them. And one of them is constructing a power set of a set. So what is a power set? The definition says that a power set of a set is a set of all of its subsets. So think about it this way. Suppose you have a set of two elements. Let's say you have a box with two chocolates, a dark chocolate and a milk chocolate. So there are several options, 4 options of what you could do. You could eat all the chocolate yourself and give me no chocolates. You could eat the milk chocolate and give me the dark one. You could eat the dark one and give me the milk chocolate, or you could give the whole box to me. So here are 4 possibilities of what you could do with the set of 2 elements, a dark chocolate and a milk chocolate, and those 4 together form a set that's called the power set of, in this case, the set of chocolates. So one important thing to remember about the power set is that the power set has sets as its elements. So if your original set A had numbers or chocolates, the power set, if you kind of open the box representing your power set, you're not going to see chocolates. You're going to see boxes. An empty box, a box with a dark, a box with a milk, and a box with both. If your set has elements 1 and 2, its power set will contain 4 elements, the set containing nothing, the empty set, a set containing just 1, a set containing just 2, and the whole set A. So in general, here is very easy way to figure out whether you constructed power set correctly, whether you've forgotten everything or not. If your original set had cardinality n, had n elements, then its power set has 2 to the n elements. And in order to see that, think about a truth table where every time you look at a assignment to variables, you think of them as, is this variable has a value true or not? Think about every assignment as a set of variables that have the value true. So you will have, let's say you have 3 variables, you will have true, true, true. That's your whole set. Or you will have true, true, false that only contain the first 2 elements. And just like the truth table has 2 to the n lines if you have n variables, the power set of a set on n elements has 2 to the n elements. So here are some examples. So we already looked at the example when you have numbers 1 and 2. So suppose your set A is empty. What is the power set going to be? Well, it's going to be a set containing the empty set. Wait a moment, is it the same thing? Not really, and actually not at all. An empty set contains nothing. The power set contains 1 element, 1 empty box that happens to be the box containing nothing. So if you open the set A, there is nothing inside. If you open the power set of A, you see an empty box inside. So let's look at another complicated looking example. What if the set A itself contains 1 element that's a set? You know, that's not going to make a difference for building a power set. So you have a box that contains 2 things. One of them is a box and another one is not a box. Doesn't matter from the point of view of the power set. You open a box and it contains 2 things. And now you can make all the combinations of those 2 things and put those combinations into boxes and put all of those resulting boxes into one big one that's a power set. So here you have two things. One of them is A, and another one is a set that's a box with 1 and B. The power set will contain the empty set. It always does. The empty box is always there. No matter what elements you have, you could make a set with nothing. It will contain the first element, A, or I should say it will contain a set with the first element, A. It will also contain a set with the second element, 1 and B. And notice that when I wrote A, I put brackets around it to indicate that if you open the box of the power set, you're not going to see A, you're going to see a box with A. Similarly, you're not going to see the box with 1 and B. You're going to see a box which, if you open it, you see another box. And if you open that inner box, then you're going to see two things, 1 and B. That's why you write two sets of curly braces around 1 and B. And finally, the whole set A containing A and a set 1B is also in the power set. So again, here is how you could write a power set. Look at all the elements, write an empty set, write every element of A with curly brackets around it. Even if it already has curly brackets, put another set of curly brackets. Now look at every two elements, or maybe the whole set in this case, put curly brackets around it. If it doesn't, if it's the whole set, then you already write it with curly brackets and put them in. So now let's look at a different way of constructing sets, which is, I wouldn't say related to the power set, but again, it lets you construct bigger sets out of smaller sets. But the construction is quite a bit different, and you get things that don't look like elements of the power set. So this is a Cartesian product. And we already seen it a little bit, although we didn't call it that, when we talked about relations. So what's a Cartesian product of two sets? It's a set of all ordered pairs of elements, with the first element coming from A and the second element coming from B. For example, if your A has element 1, 2, and 3, and B has elements A and B, then their Cartesian product will contain pairs 1 and A, 1 and B, so all the pairs with the first element of A, 2A and 2B, all pairs with second element of A, 3A and 3B. And often we write those Cartesian products in a table in a matrix form like that. You could also take a Cartesian product of an element of a set with itself. In this case, you get, for example, if you take the Cartesian product of the set AB with itself, you get AA, AB, BA, and BB. And here, notice that I am using round bracket instead of curly bracket to put around every pair. And this is very important, because if I write B equals curly bracket A, comma B, curly bracket, I mean, you could check that A is there, you could check that B is there, they're there, but they're in no particular order. The thing that you could do with the set B, it's a set, so you could say that there are two elements, and you could say that one of them is A and another one is B. When we are talking about a pair AB, like the one that's an element of B Cartesian product with B, it's a very different story. We have A first and B second, and that's different from B first and A second. And every one of those is not a set, but a pair. We could say what the first thing is, what the second thing is, but we really consider each one of them as a point. So this is actually where the word Cartesian comes from. You might have heard of Cartesian coordinate systems, or at least you've seen it drawn like that. And in the Cartesian system, you have x-axis and y-axis, And you know that the point 2, 3 and the point 3, 2 are very different points. Every point in the Cartesian coordinate system is a pair of two elements, is a pair of numbers, and the order here matters. So, for example, if you have numbers from 1 to 3, you could get the point 0, 1, you could get the point 1, 0, they would be different points. You could get a point 0, 0, that would be a separate point, which is different from a number 0. Number 0 does not belong on the Cartesian plane, really, it doesn't denote a point. So again, to reiterate, if you want to visualize a Cartesian product of two sets or even three sets, think about a coordinate system and think about every pair as a point. And also because of this construction, if you want to know how many elements are in the Cartesian product, the way to calculate it is to multiply the number of elements in A by the number of elements in B. For example, in that A, 1, 2, 3, and B being AB, the number of elements is 6 because for every element of B, there are 2 of them, you have 3 possibilities because there are 3 elements in A. So in general, we could have a Cartesian product for any number of sets. And again, think about now 3-dimensional space when you go x-axis and y-axis and z-axis. So your points are described by a triple of numbers, or in general just triple of elements. And the number of points is a product of sizes of those 3 sets. So notice that here product of A times B times C is not the same thing as A times product of B and C, because in the second case you would be taking cross product, Cartesian product of 2 sets, second one of which would contain pairs as an element. So you would end up with something different. Okay, so let's again, as a sanity check, see how we could check whether what we got as a power set and Cartesian product actually is the right thing. So the power set is a set, elements of which are also sets. So it's a big box, you open it and you see a whole bunch of small boxes inside. You see nothing but boxes. If you are writing a power set of a set, double check that you have the empty set, it's always there. Double check that you have your original set, it's always there. Check that you have curly brackets around everything. And if there were curly brackets around an element of A, put an extra pair on it. And then count how many you got. You need to have 2 to the number of elements in your original set. Now, if you're doing a Cartesian product, it's a set of points or pairs of elements. Or it may not be pair. If you have k sets, k dimensions, it may be a list, an ordered tuple of k elements. But in general, they're not going to be sets. They're going to be points where the order matters. So here below you see what the power set kind of general outline looks like and Cartesian product general outline looks like. Cartesian product is not going to have an empty set there. Unless one of your original sets is empty, then the whole Cartesian product itself will be just an empty set. Not a set containing an empty set, just an empty set. And again, to differentiate it, or to think when you need to differentiate it, think about a program that somebody written to which you give an input. If it expects as an input a point in space, then you need to give it a pair of numbers in round brackets. If it expects as an input a set, you give it 2 elements in curly bracket. If you give it something different, it will give you an error.